Hello, welcome back. So today we're going to do the application number 10, which is a teapot. This now enters into this phase of other topics. So we've gone through static problems in Abacus, we've done dynamic problems, we've done a combination of both of those using multi-steps, and now we're entering into some other things such as frequency analysis, thermal analysis, and some other interesting dynamic problems that we'll look at later. This teapot application starts to look at the thermal problem. You basically can do things, think about thermal problems in two ways. Thermal, where it's just sort of heat transfer. So it's the equations associated with heat transfer that we're going to go over eventually in our theory. And then you can do coupled problems where you actually have a thermomechanical component, meaning that the thermal problem tends, like expansion, causes deformation and strain, which leads to changes in your mechanical problem. So you can have those coupled. So we'll get to that eventually also. We're going to start by looking at boundary conditions, basically conduction, convection, radiation. Abacus can actually handle all these things, and so that's the purpose of today. Uncoupled heat transfer problems here. This information is just actually from some Abacus documentation, and the uncoupled heat transfer problems are those in which the temperature field is calculated without consideration of stress and deformation, just as I mentioned. Or you could also consider the electrical field. And it concludes these different types of heat mechanisms. They can basically, what we're going to do is look at applying convection or the heat equation to the material, but also in this application we actually do things across materials. So for example, we're going to have a lid on a teapot and we want conduction to happen between contact surfaces. So that's kind of interesting. We're going to be doing that. In this application, we actually have both transient and steady state heat transfer. So in our case, we're going to have a multi-step where we do a steady state to bring everything up to temperature, and then we evaluate how that part cools down over time. And then you can have both nonlinear and linear materials. And we're going to use heat transfer elements, and the theory will actually go over in the theory section of the class as well. So with that, why don't we go over to ACI, the portal, and get started. Okay, over on the portal, go ahead and open up a terminal, and we're going to cd into work, classes, ME461, and in that directory I have you're going to make a directory, make dir app 10. I already have one, so it's going to complain about that, but then go into that directory and you should have nothing. Okay. The next thing we need to do is get some files over there. So we're going to go back to Canvas and we're going to download the CAE file I provide to you. You can also do the PBS script and the Abacus teaching license. Okay, so grab those here, just click those to download. We'll then go over to the File Explorer on the portal and upload those. So I have to navigate into that directory. App 10. You can see I actually ran this already. I was doing some testing. So you can just drag and drop those into the directory. Where did downloads? Okay. So CAE and meters. Okay. All right. Okay. So once those are done, you can rename it here, and you want to rename that, so rename, just make that V6, say OK, and you should have the teapot in meters CAE file. All right, so now let's go back to our terminal. We want to make sure you can do a you can do an ls and make sure everything is there, and then we can load Abacus. BGL run, Abacus CAE ampersand. All right, once that's open, I'm going to just set up my graphics options here. Okay, we're going to open that CAE file. So you don't have to import, you can actually just open. So in this case, what it's going to do, it's going to give you a comment that says, hey, this is an older version. Do you want to convert it? So say yes. And say OK. And it should work. I haven't had any problems with these conversions yet. You get two parts. You get a teapot and you get a lid. Okay. Now, in the packet, I explained this, but this is actually a famous geometry. This teapot geometry is in the CAD world since the early 70s, and it's a famous object. So it's called the Utah teapot, and it's used for rendering and sort of computer graphics to test certain things. So it's kind of a famous thing there. All right, so we're going to start by we imported the part, and the units are in meters, so we should be good to go. We're now going to create some materials. So let's go to Property. And we'll create one, or just do steel, and we'll give it some elasticity. Although we don't really need elasticity since we're just doing heat transfer, but we'll just do 200 e to the 9 and 0.3. Okay, we're going to give it some thermal properties so we can select connectivity. And here we're going to go with a conductivity of 1.8. Oh, sorry, that's the next one. So we want to go with a conductivity of 20 watts per meter centigrade. So basically what we do is we're going to define two materials, a steel and a porcelain. And then you can study like how well the heat transfer occurs in those because of these different values. So we have conductivity. We also need the specific heat. So we have a specific heat for steel of 486 joules per kilogram centigrade. We also need the density, so 7,800. And that's about it. So these values are based on 1.5% carbon steel, and I provide the link of where I got that from. Because eventually I had to do some checks with this material. Like I was a bit confused about what the heat transfer was doing. So that took a little bit of figuring out, and I wanted to make sure I put that link there in case you see something I did it wrong. But I think this is okay. So we have elasticity, which we don't really need. We have conductivity, specific heat, and density. All right. So let's do one more material. We will do the porcelain, which is basically like a ceramic. What did I call it? I didn't say. So yeah, porcelain. So we'll just call it porcelain. Porce. And we need to define a density. That's going to be 2300. We're going to have a conductivity of 1.8, so the thermal conductivity is much lower, and the specific heat is higher, so we're going to have a specific heat of 600 joules per kilogram centigrade. We have density, conductivity, and specific heat. We can say OK to this. And we now are going to create sections. So we need two of these for our two materials. Okay, let's make that steel and make another one. Okay, that's the porcelain. Okay, we'll then assign the sections to the parts. So what we're going to do here is let's do the steel first. So we'll just box select, say done, and this is going to be steel, and then we have to do the lid. So we will box select again and steel. Done. Okay, so we're done with our properties. We'll then go to the assembly, and we can just take the default. So you can just select both of these with your left mouse button and say OK. So there's our assembly. We can then create a step. So you can click on Create Step, and we're not going to do static general. We're actually going to do heat transfer. So this is a new step for us that we're doing. We can name this steady state if you want. Steady state. Continue. All right, so this is going to be, the response is going to be steady state. And it says the load variation with time has been changed. Fine. The time period is 1, so because of steady state, like time, similar to our static general, it doesn't really have a real meaning. It's just basically before and after the load is applied. Okay, we can say okay. The next thing we can do is create another step. So this is going to be after the steady state one, and we're going to do another heat transfer, and that one's going to be transient. Okay, so we're going to basically heat everything up in the first step, bring everything up to the temperature we want, and then the transient step is going to be where the cooling occurs, basically. So the time period, we have to put a real time in here, so that's going to actually be 600 seconds, so it's a longer simulation. We're going to have the incrementation. We're just going to help it a little bit here to converge. So we're going to actually start with an increment size of 0.1. The minimum will be 0.006 and the maximum is 600. And then we can say max allowable temperature change per increment. Okay, so how fast does it change to get through that? And we're going to limit that to 5. So 5 degrees. And I think that is it. So we can say OK. We can pop into the field manager here and just check. So we have this field output manager. If you double click on this, you'll see that we're asking for the heat flux, the nodal temperature, and the reaction fluxes. So that's okay. We're actually going to be just studying the nodal temperature. So we say OK to that and dismiss. And one other thing, we want to do the history output manager. I noticed before that we get some, if you don't do this, it's not imperative, but you get like a little error message when you start it. So we'll just add some history to this. We'll do that in the steady state so it propagates through. And what kind of information would we want to know? Let's do time integrated heat flux, time integrated HTL, heat flux load. Okay, so we'll just go with that just to give it something to plot about. All right, so we'll say dismiss. All right, so we have our steps defined. The next thing we can do now is go to the mesh, and we'll create a mesh here. We can seed the instance. Actually, we have to go to the part, do one each at a time. So for the lid, we're going to, approximate global size is 0.0054. We'll actually keep that. So say apply. The one thing we know is Abacus tries to force hexahedral meshes. So let's go and override that and make sure it tries to do tets, because this is a complex geometry and actually hexes will fail. So we'll go with tet, and we can just say mesh now. Okay, it takes a little bit of time, and there is our mesh for the teapot. We can go in here and we need to assign the element type. So we'll box select the lid again, and you see it's stuck on 3D stress. So we actually want to go down and set this to a heat transfer element. So this is a 10-node quadratic heat transfer tetrahedron, and that's what we want to use there. So we'll say OK to that, and we'll now go to our next part. We'll seed this part, and we're going to use 0.008, and we'll also assign a tets to the mesher for this. Go ahead and mesh. Okay, and then we will assign the element type again. Say done, go with heat transfer, standard quadratic. All right, so our meshing is complete. The next thing we can do is go to the interactions. Okay, so the interactions is an interesting thing. So basically, let me go to assembly instances and hide the lid. So hide this. So what you notice here is we actually have a line in the CAD. You see that line? So we're going to basically fill the teapot up with hot water, and then our initial step is going to heat everything up in the teapot according to that boundary condition we put in there. So basically, throughout this internal surface you see, we're going to put the temperature 95 degrees centigrade on there, and then the transient step lets that cool down. Okay, so we're going to start the cooling of the teapot. So to do that, we're going to do boundary conditions, of course, through the loads, but then what happens at the interface of like how does heat escape the teapot? How does heat transfer from one part to the other? So across this interface into the lid. And that's kind of what we are doing in the interaction module. All right, the first thing we're going to do is handle conduction between the teapot and the lid. So the packet, you can see it goes through a bunch of ways. One of the things we talk about is how you make selections and how you make selection sets. So I walk through that. You can I'm going to show you an alternative way, and that is just hiding things. So there's multiple ways to do things in Abacus. So we're going to start by creating an interaction, and we're going to go with surface to surface contact in the steady state step. Okay, and so we will, and this will actually get propagated. The conduction between those interfaces should happen in both the steady state and the transient. Okay, so we want that to propagate, so we'll select the steady state step, and then it says select a master surface. So for that, what we're going to do is we're going to select the inner rim of the teapot here. Okay, so you can see if I hover over that, I can select that, and it's kind of like 3 levels that you want to select. So those are our 3 surfaces. So I'm going to say done there. That's the master, or the primary surface, I should say. And then choose the slave or secondary type. So we'll go with surface here. And then I'm going to turn my lid back on, show, and I'm going to hide the teapot. And then I'm going to select these surfaces that you see here. So hit X, and then I can just hover over these, holding the shift button down, and select that lip. All right, so we say done, and so that brings up the edit interaction button. Surface to surface, that's fine. The one thing that we're missing here is an interaction property, so we actually have to create one of those. So we will select this interaction property, which takes us to the screen that we usually get. And here we want to select the contact condition. Go ahead and say continue. And instead of mechanical, we actually want a thermal contact. So we want thermal conductance. And in this case, what you have 2 options for this. You have a clearance dependency or a pressure dependency. So you can put the conductivity based on how much pressure is exerted, right? So as you push harder, you might have more conductivity, a nice tighter surface. In our case, we're not going to do that. We're just going to do the clearance. So if the teapot actually is lifted off, the conductance changes. So you can do, and you can actually do both of these if you want. So that's kind of interesting. So what we're going to do is set this initially to 0.1. And so at 0 clearance, the conductance is 0.1. That's really small. Remember, our conductance in steel was 20. So I want to demonstrate something. So we're going to run a job, look at it, and then run another job. So we'll start with 0.1 at 0, and then the conductance is going to be 0 when we lift that lid off, and we'll say that's going to be equal to 0.002 meters. Okay, 2 millimeters. All right, so there we go. We can say OK to that. So that is our interaction property, and so we are good. So right now we could actually, after we put a boundary conditions on, we could actually run this model, and we should see conductance across that interface. All right, our next contact condition we can do is the convection with the external air. So this is how you would see heat loss occur on this teapot to the external environment. Okay, so you basically have a heat sink of like 20 degrees around room temperature, roughly 20 degrees around the teapot. So we're going to create a film condition. So we're going to go into add another contact. In this case, we will do steady state. That's fine. And we're going to say a surface film condition here. Say continue. And then it says select the surfaces. So here we're going to select all the external surfaces. You can go down to surfaces here, and I don't think I have one created yet. So what we can do is we can go ahead and make those surfaces as I outline, or you can just select using shift, and we'll just select all these surfaces. Okay, and this again, this is radiation to the external environment, so it helps cool the teapot down. So if you miss one, you know, it's air, but it's not the end of the world. All right, so there's my surface film, and that's probably good. So we'll say done. And then you have this, the definition of embedded coefficient. So you have a couple of different options you can go there, but we're going to go with embedded coefficient, and we're going to select the film coefficient of 0.5. This controls how much importance that has, kind of. And then the sink temperature is going to be equal to 20. So that's roughly room temperature, and that will be ramped and uniform. All right, so we'll say OK to that, and we'll see some additional squares put up to the teapot. Now there's one more heating mechanism we can incorporate, and that is radiation. So that would be radiation from the teapot to the ambient surroundings. So we can do that by adding a brand new interaction, and there you see surface radiation. So say continue, and then again we have to select our external surfaces. We probably should have made a set, so sorry about that, but I'm just going to select them here. I might be a little faster in this case. Oops, okay, well, I wasn't quite done selecting, but all right, you want to select all the surfaces. I'll come back and edit that in a second. But here we want to do the emissivity of the teapot, which would be 0.9, and the ambient temperature is 20. And we can actually, we have to be careful about this because this should actually be not in the correct step. So we're going to have to change that. So we're going to just say OK to this. And then I'm going to go into that manager and actually tweak this. So this is my radiation one, and I'm going to move right. So now it's only occurring in the transient step. I forgot to name that, but step 2 is a transient. And I'm going to edit this. And when I do that, I have the ability to edit the region. So I can say continue, and it will let me select in viewport. So I'll go back and reselect this stuff, I guess. To zoom in. There we go. Holding down Shift while I select that. You can even select that one if you want. All right, so that's good enough for external surfaces. Say done. And now you see that we want this to be instantaneous. So I think that's good on this. We can say OK. All right, so that contact condition is now implemented. There's one more thing we need to do in order to make this work. Note that the radiation capability uses the Stefan-Boltzmann constant to convert, because we do things in terms of Kelvin. So we need to edit our model attributes here. So what we can do is go to Model and then go up to Edit Attributes. And then here we can actually select or specify some physical constants that that the radiation model needs. Our units are in centigrade, so we need to create the ability for Abacus to use the radiation constants with that radiation effect. So we need to put in model teapot edit attributes. Absolute zero temperature is going to be negative 273.15 as the absolute zero temperature. Okay, and then we're going to add in Stefan-Boltzmann constant. So that is 5.67 e to the negative 8 watts per meter squared per Kelvin to the negative 4th. Okay, so that is what we need there. 5.67 e to the negative 8. Okay. So okay to that. All right, so now we should be good. So the next step we can do is go into load and apply our boundary conditions. So we're going to go in here and we're actually going to turn the teapot. We're going to put the thermal load as the hot water inside the pot. We're going to fill up the pot. So we'll go to lid and turn that off. We're going to hide it so we can sneak in there. And then we're going to go to load and we'll do in the steady state, we'll do a temperature, say continue, and then we'll actually just select from the viewport. And here you want to select the bottom where the water would sit. Okay, so I have that selected, and we can actually go in and select, you know, the water would be filled up. So select that, that, and then I'm going to rotate it around so I can see. Okay, so you can see the water goes all the way up top to that dividing line we have in there. So that's good. We're going to say done, and then the magnitude here is going to be 95 degrees. So we're going to bring everything up to 95 degrees and say OK. Now if we open that manager up, we see that it created that loading in the steady state, which then gets propagated to step 2. We can then edit this, okay, and this is going to be a transient step where its magnitude is a 95, but we want to decrease this over time. So we're going to apply actually we're going to try to simulate an exponential reduction of the internal temperature, okay? So in order to do that, we'll create a amplitude. So you can click on this, create amplitude, and we're going to do, we've done this before in our explicit loading, but we're actually going to do a new feature here, which is decay model. And then we're going to include the initial time, the initial amplitude is going to be 20. Our max amplitude is 75, and the starting time is 0, and the decay time is 100. Okay, so it just defines a curve, and that's going to, time span is going to be over the step time. So we say OK to that, and then we can select that amplitude. Now, what does that amplitude look like? Well, you can go up to Plugins, Tools, Amplitude Plotter, and we get this one that we just created, and we can actually plot that. And what you see here is what it looks like. So we actually have a high temperature, close to 95 initially, and then that decreases, near 400 seconds, the temperature decays. Since we have that set at 95 degrees, we don't need this also to be 95 down in the boundary condition. Okay, so we'll actually close this plotter, and in the edit boundary condition for this step 2, which is the transient, we'll set that as 1. So this is going to be 1 times that amplitude. So it's already going to take it back up to that temperature. So we can say OK to that, and we see that it's modified, so we can dismiss that. Okay, so the next thing we want to do is go into our predefined field, and we're going to do the initial and step, and we're going to do a temperature and say continue. And we're actually going to turn our lid back on, show, and we'll fit that viewport, and then we're going to select everything. So we're going to initialize this initial temperature through direct specification equal to 20 degrees. And then we can say OK. All right, so I think we're ready to go ahead and create a job. So what we can do is do a file save as, and you can save that as app10 CAE. Okay, and then what we'll do is, why don't we create a job, and why don't we do a model, a data check before we submit. Because this job has a transient step, it can take some time. So what we're going to do is submit this using a PBS script. So we'll go ahead and go over here and get our tiles arranged while that's running. We will open a new terminal, and we're going to SSH into ACIB, SSH-L, your username, and it's going to be aci-b.aci.ics.psu.edu. Once we're in there, we'll navigate to our directory. And we can go back to our Abacus. We see that the check completed successfully. So we might as well try it. What we'll do is we'll write the input. Okay, so that's going to be job1.inp is the input file that we got. And we will go back to look at our PBS script. So we did download something, gedit abacus _app10 .pbs. So we're using 2 processors for 2 hours. We can probably set that to 1 hour. And then module load abacus, this looks correct. Our job 1 is correct, and 2 CPUs, this matches this number. So this should be good to go right now. So we're going to go ahead and save that, and you can close it. Go back to our ACIB window, and we can do Q sub minus capital A. We're going to use the open Q, abacus _app10.pbs, and enter. So we get our job number or ID. We can do qstat minus u, your username, and that tells you that it was submitted and it's in the queue. Okay, so what I'll do is I'll let that run, and in the next video we'll come back and post-process.